Okay, let's try and do a quick little overview of groundwater. So I'll run through the PowerPoint here kind of quickly. I'll just try to do a little synopsis, and then you can look at the PowerPoint on your own if you want to clarify a few things. So if we were looking at where the water is, so we did this in the rivers PowerPoint. So you can go ahead and take a look at that. We can see where the ranking is. We were kind of made aware that streams, rivers, they don't make up a lot of water when we talk about the whole amount of water on our planet, especially fresh water, which is really what we're concerned with. We know that lots of water is available. Of course, we have big oceans, but for drinkable water or things we want to use water for, it doesn't really work for us. So there is a lot of water in the ice caps, so frozen water, certainly there. Once again, it's not readily available, so we want to look at water that we can use. And we can see that if we're not looking at ice, we have, our groundwater is making up, almost 94% of all the fresh water that's available. And so it's a lot. So we want to be able to access it. Of course, we want to know where it is. And we want to know how to protect it. And so we're going to kind of cruise through a few of those things in this PowerPoint so we can take a look at what's going on. And even here in Arizona, and this is kind of throughout the U.S., we rely heavily on drinking water to supplement our water resources. And here in Arizona is no different. And so we can kind of go through what we've done before in the PowerPoints. Why do we care about our drinking water? Well, certainly we need it to survive, especially here in Arizona. And water contamination is a big problem. There's some issues that arise from groundwater moving through the subsurface. We'll talk just briefly about something like this. The term karst is just a general term that describes areas that have been dissolved. So certain rocks react to the water that moves through them. And as a general rule, water is slightly acidic. And we're talking slightly acidic, so not like it's going to hit your skin and burn you, but over long periods of time, it can dissolve limestones. And limestones are a fairly common rock. And in the subsurface, as the water moves, it can slowly dissolve them. This is how we get caverns and things like that, cave systems. So if you've ever been to Kartchner Caverns down in Tucson area, it's the result of, at least part of that cave system is the result of dissolution of the limestone over time. And those caves can collapse or cave in, and then we can get sinkholes. So we can talk about that briefly, and of course it's something that we care about. So when we look at how groundwater fits in with the big picture of our hydrologic cycle, we talked a little bit about this with the rivers, of course. And so here we can see that the water that ran along the surface, those are our rivers that we talked about. There's a component of the water as it reaches the ground that does percolate or sink into the subsurface and gets stored in the ground. This is groundwater. And of course, in the ground, the water is actually moving, and it has we have the ability to pump that out. So we can put wells into the ground. And in some cases, we mechanically pump the water to the surface. In other cases, it flows freely to the surface. So we want to kind of look at how that works. So when it infiltrates down into the ground, of course, we need some way for it to do that. Now, gravity is the driver here. It's pulling the water down into the subsurface. But we need some open spaces for the water to move through. So it doesn't infiltrate in every material. Certainly there's some materials where the water hits the ground and there is no open space, and so the water flows along the surface until it can find an area where it can infiltrate, sink into the ground. And we can define the groundwater table as the point which all the open spaces below that line are full of water, and above that line, they're not full of water. So you can see in this diagram here that as the water sinks down, it moves into the open spaces. Although not shown here, typically there's a unit down here, a layer, that is not porous, does not have open space. And so it'll sink down till it hits that layer, and then it'll start to fill up all these open spaces up till a certain level. And this level here where there's this difference between all the open spaces being full of water, and not is what we're going to call the water table. And when we drill a well into the ground looking for groundwater, what will happen is, of course, this will be some pipe that's drilled into the ground, but we'll actually perforate the pipe here where the water is, and so it'll flow into my well, and its level will be equivalent to the groundwater table. This is how we can get some information about how deep water is in certain areas. We can drill wells, the wells fill up to that level, and then we know where the water is in the subsurface. Okay, what else we got for you? So a couple terms that we want to make sure you're aware of. So porosity. What is porosity? It's just the amount of open space in the rock or sediment. So in this little picture here, and you've seen this from when we talked about sedimentary rocks, material is weathered, it's transported and deposited into layers. When it's just sediment, like the first picture here, right, there's a lot of open space here. And depending on the size of the rocks and the shapes, I can have a lot of open space or a little. But over time, we certainly kind of crush that down and reduce a little bit. And if it remains sediment, there's a reasonable amount of open space here. So the porosity is usually higher in sediment. As the material gets cemented into a rock, in this case, let's say these are sand grains, and it gets cemented into a sandstone, there's still some open space here, though not as much as if it was sediment. So sediment is best, so material that hasn't been lithified yet, turned into a rock, is better. But there are rocks, sandstones is a good example of material that can store water. Even though it appears very solid when we look at it or pick it up, water can infiltrate into these rocks. And so we want to evaluate the amount of porosity some material has. Higher is better because more water storage if we have a high porosity. And so just some examples of materials that might have higher or lower porosity. And so we're looking for, on the image to the left there, when you have very similar size, so if it's well sorted and there's not a lot of cement, so the material hasn't been glued together yet, this is where we have a lot of porosity. On the right there, where we have a poorly sorted material, the small pieces fill in those open spaces and reduce the amount of porosity. Cement reduces the amount of porosity. The other thing that can help with porosity is fractures. So a solid rock that is highly fractured, those fractures, those cracks, they count as open space, and so we can store water in the fractures. If it's unfractured, then we reduce the porosity there. So high sedimentary rocks, right, we need them to be well sorted, not a lot of cement, and fractured. If there's a low porosity, those tend to be poorly sorted, lots of cement. And massive is just a term we're going to use to describe unfractured rock. And so when we look at porosities here, sands and gravels are the best because they're larger, they don't quite fit together. Muds are very, very tiny, and when they fit together pretty well, so there's not a lot of open space there. Sandstones are good, pumice, fractured rocks, all these things have high porosity. Now, we're going to talk a little bit about a term in the next couple slides that is related to porosity and to getting good groundwater. Pumice has a very high porosity, but it doesn't make it a good storer of water because the way the holes are created in a pumice, they are not very well connected. And I'll talk about that in just a second. And then some examples of rocks that are not porous. Okay, so poorly sorted we talked about. And then salts, right? So in, like, say, Death Valley, we deposit salts. Those crystals are intergrown. There's no real open space there. Massive rocks. And examples, remember, not fractured. So igneous rocks typically are not good for water storage because, once again, the way they're formed, the crystals intergrow. They lock together. And so, of course, there's no open space there, so we can't store water. Now, talking about how well connected the open spaces are, this is where the term permeability becomes important. And so we can't just have a lot of open space. If the open space is not connected, then the water can't move through the material and it can't store it. So we need, in order to have a good water source in the ground, we need something that's high porosity and a high permeability. We want the water to be able to move into the material, so when it rains, we want it to move in quickly and have a lot of porosity so we can store it. And then when we withdraw it, we want it to be easy to pump out. This is where porosity comes into play. So well-connected open spaces, this is great for water storage. And so both of these criteria need to be met so that we can have good water storage and places where we can drill, and then we can extract that water easily. And so once again, big open spaces, well-connected spaces, this is what we need for a good, what we're going to term aquifers. And so the aquifer is this permeability here. So you can't just have high porosity because that's not going to do it for us. We need it to be permeable and porous. And of course, some examples of that on the left. These are materials, whether it's sediment, sands and gravels tend to have both of these. Some sandstones and limestones. And of course, if the rock is highly fractured and those fractures are connected, we can store a lot of water there. An aquiclude is basically something that doesn't allow water to move through it. And so some of these examples are given here. This also, these aren't very permeable, but they're also not very porous. So they kind of fail on both levels there. So when we're looking for water storage in the subsurface, ones that have these qualities we're going to call aquifers. So an aquifer has a reasonable amount of porosity and permeability, can store water, and we can extract that water. So we like that. Okay, so we said the water table was that line where we have kind of the saturated, all the places in the rock or sediment are filled with water, and above that line they're not. And so we can estimate where the water table is in the subsurface. And there's a lot of factors that control that for sure, but if we were, let's say, to drill a well into the ground, and let's say we drilled it right here and we saw the elevation of the water table, because it would fill my well to the same level, what we tend to see is that the profile, what the water table looks like, is similar to the land surface. If the land surface slopes down, the water table slopes down. It's high in high areas and low in lower areas. And so how deep the water table is also a function of some factors, and that would mostly be climate. If there's a lot of water into the system, certainly we can fill up the material and the water table will be close to the surface. If we have a very dry conditions, like here in Arizona, we tend to get a lower water table just because there's not as much available, so it doesn't fill it up to the surface. So you have to drill a little deeper to get that water table. Okay, and this example would be someplace, let's say, back east. And we do see that in places where the water table is really high, the water table and the water in the subsurface is actually supplying some water to the surface water. So lakes and streams in the East Coast, in places where there's it's more humid and there's more rainfall, more water available, streams and lakes are perennial. They're always around. They don't run dry because there's getting some supply from the subsurface. Here in Arizona, that's not always true. There's no connection between the groundwater and the surface water, and so our streams, there's not a lot of them, number one, and sometimes they don't run all year round. And so we can look at streams like this where East Coast would be on the top there, West Coast, or at least in the desert area where we live, would be on the bottom. So in the East Coast, your groundwater is supplying your surface water and helping that stream maintain its flow, where out here you're actually losing water from the surface to the groundwater table. And so we can just, instead of using the effluent, influent, we can call them gaining streams. They're gaining water from the subsurface, or they're losing water to the subsurface. So gaining or losing streams, something we can look at, and something to be aware of when we're trying to figure out, how much flow a stream might have, and you can even relate that to flooding and things like that. So springs, we tend to see those pop up here and there, and they're just a place where the water table intersects the surface. And so in a lot of cases, it's whether you have different rock types. And so in this example here, this shale or mudstone is impermeable, so the water comes down and meets it, can't penetrate through it and builds up. But when the slope comes here and the two rocks intersect, we can get the water seeping out. We can get it from a fractured rock where the fractures come to the surface. Faults can give us this. And so big erosional features like in the Grand Canyon where it cuts down into the rock and exposes some rocks. You can see here we have springs seeping out the walls here. So there's a variety of ways we can get the water table to intersect the surface, and when it does, water seeps out. We're just going to call that a spring. So groundwater does move in the subsurface. We kind of argued that it mimics the land surface a little here, so high, it's higher. As it comes down, it's lower. And what that means is it's going to flow like it was if it was on the surface of the earth. So it's driven by gravity, just like we see surface water driven by gravity. And so if it's high in some area and low in another, that means that the water here is moving in this direction. It's flowing downhill. And so it's always going to flow that way. And so as we drill into the ground and we estimate the elevations of the water table, we can get a profile of what the water table looks like. It's high over here, it's low over here. So I know that the water in the ground is going to flow from the high areas to the low areas. And that can be useful when we're talking about potential contamination of groundwater. We want to know where's the water going. And so it's where's it going to bring my contaminant? Is it going to bring it to your house or someone else's place? If we know what the water table, the surface of the water table looks like, we can estimate where the flow is going. And it has some speed in the ground, usually meters per year, and water might move, a couple hundred meters every year. But that depends on how steep the slope is. So think of it like the surface of the earth, right? Water on the surface. If it's steeper, it's going to flow faster. That should make some sense, right? And then in the subsurface, there's another factor. That's the permeability. So how well connected those open spaces are. It's very permeable and the water can move through pretty easily. And so that would help with the speed of the water in the ground. Okay. So as an example, what we would do is, let's say that these little dots here represent wells. And we've drilled into the ground at each of these locations. And the number you see is the elevation of the water table above sea level. And so it's just like making a topographic map. When we talked about topographic maps, we said we know the elevation at the surface of the earth, and we can just measure that. And then what we would do for a topographic map is we would connect points of equal elevation, and then we could say, hey, look, over here, this is a high area, down here is a low area, and we can figure out, like, say, if we're going to go hiking, where's the high point, where's the low point? Well, for the groundwater table, remember, it mimics the land surface. It is a three-dimensional surface here, so it's going up and down. We can figure out its shape by, number one, identifying, where the high and low is, because remember, we said the water's moving in the subsurface. And so we know it moves from high to low. And so if we draw some lines that contact or connect points of equal elevation, these are contour lines. But in this case, they're contour lines of the water table instead of the surface of the earth. Okay, and so this is a very basic, little demonstration. The other thing we want to be aware of is we can determine the direction the water in the subsurface is flowing. It flows from high to low, we know that. But the red line here is what's called a flow line. Now, a flow line is always going to be drawn perpendicular to the contour lines. And so remember, this is a right angle, 90 degrees. And so if I was trying to figure out where the water was moving in the subsurface, I would not want to draw my line over this way, even though it is higher here and lower here. The water, if it was put into the ground here, or let's say a contaminant, it's going to go perpendicular to these contour lines I've drawn, which means it's going to flow down in this direction, not just right over like this. And so this is why it's important to have well data and to constantly monitor them so we can get a shape of our groundwater and see where it's moving in the subsurface. Once again, this is really kind of important when we talk about contamination. Now, we can use that to kind of figure out, like I said, who might be polluting and things like that. The good news about Arizona, it is super dry here, of course. We use a lot of groundwater. The good news is we have a lot of groundwater. Now, why is that? Well, it's because we have a lot of sediment available, and sediment tends to be more porous and permeable, and we can store a lot of water. So although I know you can't really read some of these values on this little image here, but this is depth to bedrock. And bedrock is just solid rock. In this case, it would be impermeable. So this material here, this kind of shading that's got the little diagonal lines, these are hard rock. And everything in between is sediment. And so a lot of these basins here are filled with sediment. And what this map is kind of telling us, it's a contour line of the sediments. And in some cases, the values, over here are greater than 10,000 feet. Some of them are unknown depth. And so that means in some place we have 10,000 feet of sediment. And so that can be used to store water. And so that's useful for us here in Arizona. And so if we were to kind of look at something like this is this example of where's the water flowing. So the lines here are contour lines, but they are not of the surface, they are of the water table. And so we can see that they're high up here and low here. So as a general rule, we would argue that water in the subsurface is kind of flowing to this bottom left-hand corner. But we can be more specific than that. Let's say this is where you live and you're getting some contamination in your waters. Let's say you drilled a well and you're pulling water up for your house and you discover there's some contamination in it. We want to figure out who might be polluting your water. Well, we can certainly make one observation, and that is that this place here, which is lower elevation than your house here in the ground, means that they can't be your polluter because the water can't flow uphill. And so we can eliminate this one. But now we want to figure out which one of these might be doing it, and how we would do that is based on our contour lines. We're going to draw flow lines that are perpendicular to those contour lines. We can see that the Acme battery can't do it. And even the Evil Empire here, if we draw the lines as best we can perpendicular to those contour lines, we can see that it's, even though your house is at a lower elevation when we talk about the groundwater table, it's going to move past your house and not intersect your well. Where the dreaded manure company, not so much, right? So this is super basic, but this is really how we attack certain contamination problems, to figure out who's polluting, how fast it's moving in the subsurface, so that we can develop some plan to fix that issue, right? This is just a general kind of cross-section, a side view. If we're going, let's say, from kind of the Luke Air Force Base area across, so it's kind of an east-west profile to Apache Junction, you can see that there's some impermeable bedrock down here, and there's these basins in between, right? And this is a little exaggerated just to give you an idea. And so there's a big basin over here, and so there's different types of material we can identify, each with their own properties, and different water types are available in there. Some are more pure or cleaner than others. We can drill wells into all these open space materials and pull water out and all good things like that, right? Okay. And then once again, just a water table elevation. And these change over time. So as we pull water from the ground, we cause the water table to sink down. And so we're constantly changing our water table elevations and locations. If we pump a lot in some places, the water level there will drop. And if we don't pump in some places, potentially if it rains or things like that, we can increase levels of water in our water table. And so it's constantly changing. So this is why, of course, across the valley, there's hundreds and hundreds of wells that we use to pull water out, but we also use those to monitor the level of our groundwater table. And so that can give us some idea of where the water's going. Okay. A few other things. Did I say this was going to be quick? All right, I'll try to wrap it up. So you can pause, of course, anytime and take a break. But a couple other terms. Artesian wells are just what are called confined aquifers, and the example is, of course, this diagram here. So all an artesian well means is that the water in the ground will rise above the level of the aquifer. And a lot of times artesian wells mean that they flow to the surface on their own accord, so we don't have to pump them. And so if someone's saying, hey, artesian water is better for you, it doesn't mean that. All it means is that it rises to the surface without assistance. And it only does that because it's under pressure. So the idea in this diagram here is that this is the level of the water table based on this layer here. It is kind of confined. It's got a layer on top that is not permeable and a layer on bottom that's not permeable. The only way to get water into this type is in these mountainous areas where this layer is exposed. And so it can fill water. It'll come down here and fill this up, which means really the water table elevation is here. And so if we bring that across to this, kind of plain area, and you drilled into this, the water wants to rise to the level of the water table, which happens to be way up here. And so it's really under pressure, and so when you puncture into this, it'll actually flow to the surface, almost like an oil well, something like that. That's all artesian means, is that it's flowing to the surface of its own accord, and you don't need a pump or something to pull it out. And so when we talk about how we're going to manage, in a lot of places, recharge is just the surface of the earth. It rains on the surface, it sinks in. These are unconfined aquifers where there's nothing on top. But here, the recharge area is very small. And so managing how much you take out with how much goes in is a big part of how we try to, keep our groundwater from, running out. And so it's a balance that we sometimes are good at, sometimes not so good at, right? So we always want to be aware of how we're doing that. Of course, there's some issues today of not just here in Arizona, but across the world where we're pulling too much water from the ground. And over time, that groundwater table is being depleted. It doesn't refill as fast as we take it out, and that can be a problem of either running out of water or some other problems, which we'll talk about briefly. So speaking of that, here's some issues that we have with groundwater. We said that when you pump from the ground, you're depleting water that's in the subsurface, and so we can get certainly an overall depression of the water table, which means that the water table is slowly going to sink down. But right around the well, we get a depression called the cone of depression, and the more you pump, so it's a small feature here you see, whereas it's kind of causing the water table to be depressed here. In bigger wells where we pump heavily, it can be a lot bigger. And of course, this example is showing how a well like this that's deeper and larger and pumping a lot more water can affect other wells by pulling the water table down. Now the idea is that if this well stopped pumping, this would recover and go flat again, relatively flat, because it would mimic the land surface, although overall it might be lower until we added some more water to the subsurface, and that could rise, make the whole water table rise up. Let's see, some other issues. Certainly contamination we talked about as a problem, so from a variety of sources. It can be, stuff sprayed on the surface, it can be yuck, I don't know what that is, but and it can be, from industry and things like that. So sometimes landfills leak, things like that. Companies have pools of water on the surface that contain things that aren't very good for us. And if those aren't sealed properly, they can sink down into the ground. So a lot of issues that can come with that. Buried gas tanks and things like that. Luke Air Force Base had a big problem with their underground fuel tanks that they used for jets and things had leaked, got into the groundwater. Oh gosh, not good. Okay, so just some examples like we were talking about. Kind of blaze through these kind of quickly. Septic tanks, landfills, these are issues that can cause contamination to the groundwater. All right, so this isn't the yummiest. Okay, so real quick. So the idea here is we said that, remember, that the groundwater flows from high to low. And because this slopes downward here, the land surface and the water table kind of are similar. We said the water table mimics the land surface. And so here we have this high area, low area, water should flow downhill. The idea here is that if you purchased this land and built your beautiful house here, and you remembered something from your geology class that said, look, I'm going to put my septic tank down slope from where my well is, because just in case my septic tank leaks and gets into the groundwater, it should flow this direction, because that's what the land surface does, and my well will be safe and I won't be drinking poop, right? But the idea is that if someone came and bought the land behind you and pumped heavily, they could lower the water table over here, and that would change the direction of flow. And now this material, if it ever leaked, would actually flow this direction, even though the land surface doesn't show that, and that could cause some problems with your well. So pumping from the groundwater is going to change its elevation, which is then potentially going to change the direction of flow. And that's something we need to be aware of. Some other issues that we run into for coastal communities or islands, there is a boundary between fresh water and salt water. Water that hits the ground here and sinks down in is fresh water, and of course the ocean water is seeping down into the open spaces, and it forms this boundary here. And so we have to be careful about how deep we drill and how much we pump. If we pump too much, we can pull salt water into our well, and that well will be lost. You can't get it out once it's in there. And so once again, coastal communities and islands have to be concerned about some saltwater problems. Sinkholes. So this is one of the hazards we talk about certainly in our disasters class, but what we get here is water in the subsurface will, in specific cases, and a typical sinkhole is really something that forms in a rock layer what's made of limestone. And so certain areas are more susceptible to sinkholes, and it's really based on this idea of limestone in the subsurface that gets dissolved over time. The idea is that water moves through this soil layer, gets down into the rock, and flows along these bedding planes and fractures. And as it flows through here over thousands and hundreds of thousands of years, it starts to dissolve this rock. Because limestone is a base, rainwater is slightly acidic, they react with each other. And a cave system can form down here in the subsurface. Well, just because there's a cave down here doesn't mean you're aware of it on the surface. And so there's this layer of material that covers potentially this cave. But over time we build, we add weight, and what can happen is over time this layer will fail and fall into the cave as the roof collapses, and of course then we get a sinkhole that brings all this stuff with it. And so it can be fairly catastrophic, so unknown that there's a cave system down there, everything seems to be wonderful, and then a huge collapse, or it can be something that sinks down slowly over time. Florida has hundreds of sinkholes, and it's really because that whole layer there is old reefs that are made of limestone. Water in the subsurface has over time dissolved those. There's lots of open spaces and caves down there that potentially can collapse and cause problems. So the dissolving of carbonate rocks, which is what a limestone is. So let's see if we can get this thing to play. So this is just a few examples of some sinkholes, collapse features. You know, they take on different shapes and sizes. This is a pretty large one that I forget where this was at, but you know, I'm not sure if it happened suddenly, but it's a little scary if you have something that big form. In other cases, it forms underneath structures. So here they're not demoing this building. This building was actually built over a open space, a cavity, a cave, but it was unknown to them because there was a layer on top of it that was concealing it. Once they put the weight on there, over time, right, that layer collapsed and it took the structure with it. So we see things like this occur. Let's see what else we got for you. It can happen like this. So this is pretty fast. So, you know, there's this sinkhole occurring here. It's bringing structures with it. And so that could have been, you know, 20 years of perfectly fine, and then conditions change and we have the collapse of the material into that open space, and of course it depresses the subsurface or the surface here and brings all the structures with it. What else I got for you? So Florida, we said, is prone to those. There is an example of and this was crazy, there was a sinkhole that opened up under a house, and somebody was in the room where the sinkhole opened up, and they fell into this open space, this cavity. So certainly not common that this would happen, but this is not a bad little diagram to show, you know, here is this open space here, and there certainly can be water stored in there. Over time, the cave can grow, or the cavity, and the material up here that's just soil that has developed over a long period of time starts to fall into the open space. And once it reaches the surface, it can bring the whole thing with it. And then, you know, not, like I said, this is not something common that we would expect to see. In other cases, this was a resort that was built in Florida, and, you know, one night the surface collapsed into that open space and took a lot of the structure with it. And so there's a lot of examples of this. I won't run through them all, of course, but they can be kind of crazy. So we'll pause for now, and I can put a link to this, and you can go, you know, view a bunch of other sinkholes if you're interested. All right, let's go here. Oops, let's go here. And so a few other issues that we might run into is what's called subsidence. So this is a very general term that describes the lowering of the surface of the earth due to compaction. And so that can happen for a variety of reasons, but one of the main reasons is excessive groundwater withdrawal. So what we see here is that the open spaces between the pieces, right, the fragments, the sediments, is full of water. Now, if I try to crush that, if I put weight on top of it and try to compact that, that open space is actually held open by the water because I can't compress the water. But if I pump the water out, now I only have air in that open space. And over time, the weight can crush down that, and it actually causes the land surface to sink. So this is a big problem in coastal towns where you're not that, you know, high above sea level. You have open space, a lot of sediment here. It's full of water that you can use for groundwater to pump out. But if you pump out a lot of it, then the open spaces don't have water in them anymore, and the weight of everything on top can cause it to collapse, and then your elevation here is lower. And of course, if you're near sea level, that could be bad because you can get excessive flooding. And so subsidence can happen in lots of places, and it can be for also removal of oils and other fluids that are in between open spaces, but it's commonly associated with groundwater withdrawal. Let's see what else we got. Just to kind of elaborate a little bit on the subsidence story. Look, in a lot of places where there's a lot of sediment deposited quickly, that's deltas, we get this subsidence problem. And so, of course, an example of that we have is the Mississippi River Delta, and there's a lot of people that live here. Over time, this delta has grown as the river has deposited a whole bunch of sediment all over the Louisiana area and grown new land, right, that has grown out into the Gulf here. And of course, then we come along and we live on this. The problem is that this amount of sediment deposited so quickly sinks just of its own accord as we pile more stuff on top of it. But then as we pull water out of it, it makes the problem worse, and subsidence can happen even faster. And as an example here, we see this is a cross-section through New Orleans, where the Mississippi River is on one side and Lake Pontchartrain is on the other. And you can see that people are living here, and the only way they can continue to live here is that they have to build these very huge walls here to keep the water out, because in places we're below sea level. So this is all sediment from the river, the Mississippi River. It's part of the delta, and it is sinking. But of course, because there's a lot of wells in here, because the town needs, drinking water, it's pulling material out or water out, and it's causing this to sink even faster. So definitely a problem in New Orleans, and it's mostly because it's a delta, right? Okay. Other places we see a lot of subsidence is in California. And so I believe there's a video you're going to watch that talks about this problem in California. It's the same deal. In the San Joaquin Valley there, it is a big basin full of material, much like the basins here in Arizona are. Weathering of the mountains has washed material into the basin, filled them up with lots of sediment. Water comes in and fills those open spaces. A lot of groundwater there. Well, they grow a ton of stuff there in the valley, and so they use a ton of water because there's not enough surface water. And in times recently where there's been a drought, they pull a lot. And so what we see is that the land surface is sinking. And so this is an example of how severe it can be. So this was the land surface in 1925. Here it is in 1977 when this image was taken. And you could see that it's dropped, I don't know, I think we roughly like 25 feet, right, over 50 years. And so, you know, maybe 6 inches a year doesn't seem like a lot, but over time, crazy. So the good news is in a lot of places there's not a lot of structures that are affected by this. And this is an extreme example, but most of the valley has this subsidence problem. And it's really due to you pull the water out, it lowers the water table. Those open spaces can now be crushed because there's no water holding them open, and over time they sink down and we get this lowering of the land surface. Now, we get this here in Arizona too because we have big basins, but it's not as severe as we see in California. We actually get something a little different here that's related to subsidence, and that is what's called earth fissures. Now, earth fissures are cracks in the ground, but it's related to this idea of the land surface sinking. What we see is that these cracks or earth fissures tend to appear near mountain fronts like this. And so what happens is, here's my mountain, here's my basin, it's full of material. We get water that goes in there and fills it up, and we have, let's say, a high water table here. Well, if we pump it down and lower the water table, what happens is this material here can now crush down and compact. So this compacts, but over here I don't have anything to compact. So this drops faster than this, and in order to accommodate the difference in elevation, we get a crack. And so these tend to form in these locations. Any place where there's a difference in thickness of sediment, we can get earth fissures. And so the whole land surface might not drop by 20 feet. We might only get a couple feet, but that's enough to cause this crack here, this earth fissure. And so since like the 1980s, these things started showing up and people started being aware of them. And certain agencies, Arizona Geological Survey, has been monitoring them and looking for these and trying to figure out a solution to them. And certainly one of those is to regulate groundwater withdrawal. But in places, especially to the south, let's see, kind of the southeast in Arizona, a lot more because a lot of agriculture there, so they're pumping a lot more groundwater. But if you're, as we develop out that way and build homes, we have to be aware of these features because, of course, a crack in the ground like this that you see on the left here can cause damage to homes and structures, so we need to be aware of that. And here's my high-tech drawing or animation here. And so what you're seeing is as the water table lowers, now this isn't near a mountain front, but buried in a lot of times in our basins are this irregular bedrock. The basin isn't always just a bowl shape. And so here we have a difference in thickness of sediment. So as we pull water out, the land surface compacts. Over here, it can compact a lot. Over here, a lot. Over here, not so much. And so in order to accommodate the different levels of elevation drop, we tend to get a crack or a fracture, in this case, above the area where the thinner amount of sediment is. And so, of course, that leads to these fractures. So they don't always form at mountain fronts, but they're certainly more common there. But these things can show up in lots of places around the valley. once again, we have agencies trying to figure this out and identify them, and you can look at some maps about where these features are. This is a problem related to groundwater. So obviously here in Arizona, groundwater is super important. We live in a desert. We need that. We do a good job of managing a groundwater supply here. And the article that I'm going to have you read talks about how in the 1980s we had to make some new rules so that we wouldn't run out of water and so that we could manage our groundwater. So you can take a look at that. It'll kind of relate back to this. So that's really, I think, all we're going to talk about with groundwater. I don't know what short means, but 45 minutes, maybe not really short. But hopefully it's helpful. You can certainly take your time as you go through this video and do it in chunks if you need to. But otherwise, that should be enough to help you get through this module. And I will talk to you guys later.